my recorder cut me off. All I was going to say here at the end was that I'd rather not write it as 4n plus 0. I would rather just call it 4n. Moving on. Okay, the last thing that we're going to do here before we review a few more examples with geometric sequences is we're going to talk about convergence and divergence. So the words converge and diverge, what those mean, converge means like if I were to continue this pattern forever, we would say that the pattern converges if it goes to a finite number. Like if all the numbers head towards 2, then we would say it converges to 2. Diverge means if we were to continue this pattern forever, that it goes to infinity or no clear value. So it's just kind of like a new vocabulary thing for you. There's not a whole lot of math that needs to be written down for these. It's more of a conceptual thought. So if I say, here's a pattern, 1, 1/2, 1/3, 1/4, and I say, does it converge or diverge? What I want you to do is I want you to think ahead. What would happen if this pattern continued on forever, and would that value be equal to something? So this says 1/n. I don't need you to really worry about writing a formula like that necessarily, but just think about like, what's the pattern doing? Well, the pattern is 1 over something, right? So if I were to continue this pattern on forever, that number on the bottom would continue to increase by 1 each time. Let's just say we're all really far down the road and we want to plug in some number just to kind of get a feel for what's going on. So this would be 1 over some really big number. So maybe you could just help yourself think through it by picking a really big number. I don't know, like 1,000. And use a calculator to type in, like, what does 1 over 1,000 actually equal? Well, that would be 1/1000th, right? Okay, and then what would happen if I continued to increase that number on the bottom? Remember, this is like, what would the pattern look like if you were way down the road? So let's make it 10,000. Well, if you type that in a calculator, you would get 0.0001. The point is that all of these numbers as a pattern are continuing to get smaller and smaller, and eventually, if I put an infinitely large number down here, and we're just going to call it a really big number, it would be equal to basically 0, because this number is going to continue to decrease as the bottom number increases. And so because we're converging and the pattern is going to eventually equal 0, we would say that this converges to 0. We say the word converges because it's a finite number. It's not going up to infinity or something like that. Let's look at another one. So we have 2. I'm going to write them as decimals because I think that's easier for us to kind of like wrap our head around. 1.5. This would be like 1.3 repeating, and then 1.25, and so forth, right? So the question is, what's this doing? So is this going to converge or is it going to diverge? Well, let's just try to find the pattern. So it looks like the top is increasing by 1 and the bottom is also increasing by 1, but the big thing is the top number is always 1 larger than the bottom number. So I'm just going to, again, pick like a really big number. Maybe I'll just do something like 50. And if the top was 50, the bottom would be 49, according to the way this pattern is set up. So I'm going to get a calculator and I'm going to see what this equals. So 50 divided by 49 would be equal to 1.0204. And then let's just do another one. So this obviously is not the next term, but just down the road, another term would be 100 over 99. So what's that equal to? That looks like 1.0101, and that repeats. So if you were to say what this is converging or diverging to, would you agree that it looks like it's going towards 1? That's kind of what I'm thinking. So, and if you're still not convinced, you can plug in something even larger, like 10,000 divided by 900 or 9,999 divided by, type it in, and this would give you 1.0001. So all these numbers are getting closer and closer to 1 as the pattern continues. So we're going to say this one also converges to 1. Okay, a couple more. This one's a lot easier, I think. So 2, 4, 6, 8, 10. That's a pattern that's adding 2, right? What's that going to do as the pattern goes on infinitely? So if I'm adding 2 over and over again, the pattern is going to go up forever, right? It's basically going to go to infinity. Since it's going to infinity, we're going to call it divergent, or we would say that it diverges to infinity. Okay, here's our last one. This one goes -1, 1, -1, 1. So that pattern is just going to continue over and over, right? -1, 1, -1, 1, -1, 1. Is it ever going to stop at some point and end up equaling a number? Nope. It's just an oscillating pattern. So we're going to also say that this one diverges. We can't say what it diverges to because it goes back and forth, but we do call that oscillating. And we could just say it oscillates between -1 and 1. It's just not gonna, it's just gonna keep bouncing back and forth forever. All right, so we're gonna go back and do a little bit of practice with geometric sequences, writing those recursive rules and those explicit rules. And I think we're pretty much done after that. So like 2 more examples. So for the following geometric sequences, find the common ratio, the 10th term, a recursive rule for the nth term, and an explicit rule for the nth term. So the common ratio is kind of like what we did before with common difference, but it's just what's the pattern. So this is timesing by 2, right? So your common ratio would be 2. I do want to point out that there is a way to compute this if it's not obvious. So the way to compute it would be to take a term and divide by the one before it. So I could either do 6 divided by 3 to find the common ratio, or I could do 24 divided by 12, or I could do 48 divided by 24. Anything like that would give me that common ratio of 2. Fine, what's next? The 10th term. Okay, so the 10th term, we're going to follow the explicit rule. So I'm going to kind of skip around again and write the explicit rule. So the explicit rule formula looks like this. And that was on one of the previous slides. This one's a lot easier to deal with because it's basically just plug and chug, meaning what's your first term? So look at your pattern. Your first term is 3. What's your common ratio? We said 2. And you have an explicit rule. I like parentheses instead of the time symbol, but same thing. So once you have your explicit rule, you are just going to plug in 10 for the value of n, like this. And you're going to compute. And you're probably going to need a calculator to do that, which is totally fine. So this would, I'm going to simplify before I do anything else. The exponent, it looks like 10 minus 1. Well, that would actually just give me a power of 9. Okay, so in my calculator, I'm going to do 2 to the 9th power. That gives me 512. And then 3 times 512 would be 1536. So my 10th term is 1536. Okay. One more thing. Let's go back and do the recursive rule. So in a recursive rule, remember it's 2 steps. Step 1 is state your first term. So I'm going to say my first term is 3. Step 2, I'm going to state what to do to get the next term. This is a multiplication pattern. So your recursive rule is going to show multiplication. So I'm going to say, take the previous term, which we call A sub n minus 1 and multiply it by, what was it, 2? So that's telling you take 2 times the previous term. And then remember, you make that little statement saying that this is only for terms beyond the first one. So starting at n equals 2 and up. Okay, last one. Same thing. Let's just repeat. This one's just a more complicated pattern. So let's start with our common ratio. 12, negative 6, 3, negative 3 halves, 3 fourths. If you aren't sure what the pattern is, you can do the little trick I showed you, and that is take a term, divide by the previous one. So I could do negative 6 divided by 12 or 3 divided by negative 6, so on. And this would give me a common ratio of negative 1/2. So this pattern is multiplying by negative 1/2 to get from term to term. Okay, I'm going to go down and do my explicit rule because in my mind that makes most sense to do that next. And so the explicit rule says take whatever your pattern, I'm sorry, your first term is, so 12. Your common ratio goes in the parentheses, and we raise it to the n minus 1 power. There's your explicit rule. I think I'm going to go back and do the 10th term now, because now that I have my recursive rule written out. And so I've got, I'm going to write my explicit rule. I'm going to write my explicit rule, and then since I'm finding the 10th term, I plug in 10 for the n value right here, and just do the math. So 12 times negative 1/2, that would be to the 9th power. Negative 1/2 to the 9th power is negative 1 over 5/12. Feel free to use a calculator for that. And then 12 times negative 1 over 5/12, so it'd be negative 12 over 5/12, and then I believe you can divide by 4. So this would be 3 over, hold on a second, 128, I think. Yeah, that seems right. And then last thing is your recursive rule. So again, you state your first term is 12, and then you state what to do to get to the next term. Well, in this case, we're multiplying by negative 1/2. So I'm going to say take negative 1/2 times the previous term, starting with n values greater than or equal to 2. That's it. As always, if you have questions, feel free to reach out to me via email, Remind, or get a hold of me and we can do a Google Meet. Bye.